Well, Lee, have you heard that when people are lost in the wilderness, they have a tendency to walk in a circle and come back right where they started?
No.
Well, that's a theory at least. And you and I are going to do a scientific experiment to see if it's true. And you're going to get lost by putting a blindfold on you.
Okay.
Now, over there, you see that tree with the white band around it?
Yep.
Yeah. You're not, are you aimed right for it now? Okay.
Yep.
Okay. I'll walk next to you to make sure that you don't bump into anything. When I tell you to stop, you reach out and touch the tree.
Okay.
Okay? Go. Stop. You feel the tree?
No.
Oh, wait.
It's way over there.
Way over there. And you can see if you were going to walk for half a day, well, you'd go, definitely keep going to the right and right, and you might end up where you started.
Right.
But to be scientific, we should do that again to make sure you do the same thing again. So let's try it.
Okay.
So right here someplace? Okay. Ready?
Yep.
Go. Stop.
I can't feel it. It's way over there again.
Same thing, yes. Now, how about my trying it?
Okay.
Can you guide me so that I won't walk into it? We'll see if if I go off to the right too. Okay, here. Wait, I want to get a good line on the tree. Okay.
Okay. Go. Stop.
Okay. We take it off? Oh, closer.
Yeah.
Yeah, closer, almost. Now, do you know how to prevent that from happening? When you're
No.
out in the woods, if you think you might get lost, what you do is look way off in the distance and find something to walk toward. Then you walk straight to that. And you stop there and you find something else that you want to walk toward and you just walk straight for that. Because
Okay.
if you don't, you might end up walking in a circle.
It's level now, Mr. Wizard.
Okay, this means we have the two sides of the double pan balance in
Yes.
balance, right?
They're the same.
Now, what I'd like you to do is to take off this pad of steel wool with the tongs. I'm going to light this torch, and we're going to get it on fire. Okay, it won't burn, too much.
Right.
And then, after we make sure that it's out,
We have
we're
to
gonna
see
put
what
it-
happens.
Yeah, we're going to put it back on the balance. Now, so my question to you is it going to be heavier? Is it going to weigh the same, or is it going to be lighter?
It'll be heavier because, well, you're adding heat to it.
And heat weighs something, does it?
I don't know, does it?
Okay. Well, maybe we better find out. Your prediction is that they're going to be heavier.
Right.
Okay. So put on the safety glasses.
Okay.
Okay with the tongs while I light the torch.
Do you have to light the whole thing?
Yeah.
Now there's little molecules, like they're all coming off.
Well, there's something dropping off, right? I don't know if they're molecules, but...
Little pieces.
Right.
Does that mean it's going to be lighter now, maybe?
Well, you want to change your mind?
I think so.
You think so? Wait, let me give it one more blast. Okay. So you're going to change your mind. Wait till it goes out now. Wait till it goes out.
What does the blowing do?
Well, in this case, I'm blowing out the few embers that were left.
Oh.
Okay, put it back on once. And Now you can take off the safety glasses and see whether your prediction was correct.
Oh, it was. It is heavier.
Yeah, it's heavier.
Well, my first one was.
Your first one. So how come you saw things drop off? It should be lighter, right?
Right.
Well, in other words, there's more mass on this side of the balance. Where
Right.
did it come from?
The torch.
Yes, we added something with the torch. Actually, what we did is we burned it and we added oxygen.
Oh, oxygen to the-
right. Now, doesn't it seem strange that here
Yes.
is this invisible oxygen that's all around
Yeah, how
us?
come it doesn't fly off?
It doesn't fly off? Well, ordinarily when you burn wood or paper, it changes to a gas and goes floating off into the air, so it disappears eventually.
Right.
In this case, the metal was held right there, and the oxygen combined and stayed there. So we
it's-
have iron oxide now instead of just plain iron.
But it's because of the texture of the wool.
Right. Okay. And so we actually added some mass and made it heavier. So you were absolutely correct,
Oh,
except...
for the wrong reasons.
Okay. Although it looks like fun and games, this is sort of a final exam for engineering students at the University of Maine. When students are graduated, they'll face problems that can't be learned in the classroom. That's one of the reasons University of Maine has the amphibious human-powered vehicle competition. Students learn what it's like to turn an idea into a final product that works when it's built. They also learn the value of teamwork, since engineers often work together to solve problems. Economy is important, since the materials to build a vehicle can cost no more than $100. Then come the final tests. They race across the mall to test their vehicle's off-road capabilities. Finally, the big event of the day, the water race. A trip down the river to test the vehicle's stability and speed on the water. Although students compete to win points, they all gain valuable experience, learning to meet the creative challenges of designing and building an amphibious, human-powered vehicle in their unusual engineering final exam. Clara, here, this fan is going to represent pieces of equipment that go round, around real fast, or that go back and forth, and you are an engineer and you have to study what's going on. Right now you could certainly see what's going on because it's not moving.
Yeah.
But I'll turn it on, and now that it's going at such high speed, you can't see what's going on with each one of those blades. However, if you could light it up so that the light flashed on and off at the same speed that the blades were going, they'd appear to stop.
Okay.
As a matter of fact, that's what this black box is over here. It's a light that can flash at 60 times a second, and I can adjust the speed of the fan so it appears to be stopped. First of all, let me turn out the lights.
Well, it appears to be like it's stopped. Well, it's
Well,
going
it's
slow.
going on very slowly, right? And I can
Yeah.
adjust the speed of the fan to make it almost stop. Now, it looks like it's stopped, but I'm going to hold a piece of cardboard in there. Watch.
It hasn't. Yeah,
It's not stopped at all, isn't
Yeah.
it? And notice how when I put the cardboard in, I changed the speed, so therefore it went around. You could see many versions of the blade.
Okay.
Right now, you can see just 3. So if you were an engineer, you could see what's going on with each one of those blades.
Yeah.
And they use it to study things like sewing machines and drill presses and other things that go around real fast.
Okay.
Okay, let me turn the lights back on again. And you'll see how you'd have to, now you can see sort of 2 images, can't you?
Yeah.
See the one from the regular light and the one from the flashing light. Okay, now that's sort of the practical applications of it. But you can have fun with it too. In fact, sometimes they have flashing lights like that at a nightclub. Have you seen pictures of that where they flash a light?
Yeah.
It works on somewhat the same idea because people look like they're going in sort of slow motion, right?
Yes.
Because you see only images every once in a while whenever the light flashes. In this case, here is a sort of circular cardboard with a strange design on it.
It's like a circular, I don't know, checkerboard.
Yeah, like a circular checkerboard. And if we now bring the flashing light over to that, wait, let me turn out the room lights. Now there it is, without going around, and I'll slowly start it. And you watch what happens.
Okay. It looks like each circle is going in a different, different direction.
Now the center one stops, and then it starts again. And then that's because each of the circles has a different number of squares on it, or rectangles, so that depends on how fast it's going, whether they appear to be still or not based on the light. You can hear the motors making a noise, so you know very well it's going around real fast.
Yeah.
In fact, if I get it going fast enough, I can get it so that it appears to be stopped, just like the fan blades. Now watch. Almost. There we go.
Yeah, it looks like it stopped.
Looks like it's stopped. But you now know it's going around at tremendous speeds. You can hear the fan.
Yeah.
Okay, now I'll slow it down. And it should go back through those same gyrations that we saw going up.
Okay.
This is not pepper that I am sprinkling on your hand, right, Derek?
No.
Yeah. Have you any idea what it is?
Not one idea.
Well, they're iron filings, so that gives you an idea what's underneath the cardboard, right?
Uh-huh.
What?
A magnet.
Right, a magnet. And it's strong enough to go right through your hand.
Uh-huh. Looks like it's just the werewolf's hair.
All right. Like you're growing moss on your, black moss on your hand. Okay, turn your hand upside down. Because very often when you do experiments like this with a magnet, you put a piece of paper on it and you put iron filings on it in order to see the lines of force. And you can see them here, see them?
Yeah.
Okay. And now you can also see them sticking up sort of in 3 dimensions, right? A strong magnet on it. In fact,
It must be a strong magnet under there because, whoa, it should be a strong magnet because look how big it is.
yeah, well now you can go ahead and play with it like this, okay?
It's hard even to pull off.
All right.
So it must
Okay, let's get it off of there so you can take a look at that magnet. Okay, dump it over here on the tray.
Okay.
Now you can take the box off and take a look at what's underneath.
Whoa, that's huge.
That is really a magnet, right? As a matter of fact, to give you an idea how strong it is, take the hammer off.
Oh, that would be pretty. Not easy.
Really strong,
Yeah.
really strong. Now, in other words, to prevent that thing from happening, engineers and scientists, when they work with magnets, they put a keeper on it. And here's a keeper. It's a piece of metal which they put across the top. So here, put it on.
Okay.
Watch your fingers.
Whoa.
Yeah. Okay, here's another one. Okay. Now the magnetic force is going through this, so that's why they call it a keeper. Now, have you ever done any experiments with magnets?
Yeah, sometimes at school when the teacher's out of the room, we take magnets that we see on the board and we throw them against the board and we just see if they can stick, and if they don't stick, then
Okay, you call that an experiment?
sort of.
Well, yes, I would say that's an activity
Yeah.
at least, right? Anyway, so there must be some metal in the blackboard. Or is there a green board?
No, it's a black.
Black
it's a
one,
black
okay, so it's probably metal
Yeah.
covered with something so that you can
Yeah.
write on it with chalk. Well, now you began to get the feeling of what the magnetic lines of force look like in 3 dimensions, but here's a much better way over here. See that plastic box? Shake it all up. Because inside there are iron filings similar to those we had on the big magnet, but they're suspended in mineral oil, which is fairly thick, which means that the iron filings will sort of stay suspended a lot more. Okay, now put it down on here again.
Okay.
And here is a magnet. And I can stick it in a little tube that runs through the middle of these iron filings. And now you can see the lines of force much more easily and in 3 dimensions. See how they're beginning to go around each end of the magnet?
Looks just like the iron filings on
Right.
my hand.
Right, on your hand, except this time you can see them in 3 dimensions because that's the way the lines of force exist around a magnet. But most of the time you don't realize it. And now you can with this special kind of box that has mineral oil and iron filings in it and a magnet. Okay, Alan, you want to hand me another piece?
Okay, sure.
Okay. Okay, there we got it all ready to go. Now, ordinarily, kids like to do an experiment in which they put a plastic bag over a plant in the house and collect the moisture that the plant gives off. I thought it would be much better if we did it over a whole branch of a tree.
But how do the leaves let go of the water?
Well, water is coming up through the roots, up through the trunk, you know, and out into the branches and the leaves, and it's part of the whole food-making process. But there are tiny little cells on the undersurface of the leaf that control the amount of water that's given off.
Oh, it's just like us, because when we sweat, we let water out of our skin.
Well, it's perspiration, you know, somewhat like that. The process is somewhat different, but it's the same idea.
Oh.
So, well, let's leave it on all day. Come back sometime tonight, okay?
Okay.
About 7 o'clock or so?
Sure.
All right. Do you recognize what's in that can?
Yes, it's some sauerkraut and it smells awful.
You can smell it, yes.
Yeah.
Well, notice that I have a clip attached to the outside of the can.
Yeah.
And then going on here to the meter. And the other wire from the meter goes over here to a piece of copper.
Okay.
So would you please take the copper and plunge it into the middle of the sauerkraut.
Okay.
And watch what happens to the meter.
It goes up a bit.
Yes. In other words, we're generating an electric current
Yeah.
with the sauerkraut. Now,
Why with the
Well, the
sauerkraut?
reason you can do that is in order to make a wet cell like this, you need two dissimilar metals and an active chemical in between. Right now, the copper and the side of the can are not dissimilar enough. In fact, here is a piece of zinc.
Okay.
Now put that in the place of the can and watch what happens to the meter.
Doesn't. Oh, there it's going up.
See, now
a
it's
bit.
going up higher and higher. Well, it depends on how far you put in the pieces of metal because they
Okay.
need more surface to work on it. Yes.
Yeah.
Well, some people are surprised to realize that you can make a battery out of sauerkraut, but after all, it's an acid, right? You
Yeah.
recognize it.
Like in a car battery, there's acid. and
Yes, in
acid.
fact, there's a series of plates with acids in between.
Yeah.
So, wash off those two plates now.
Okay.
And I'll get rid of that, and you put the two plates here in this beaker.
Okay.
Okay. What's the reading on the meter?
0.
Nothing, okay. Now what do we need in order to make a battery again?
An active chemical.
An active chemical, okay. This time we're going to put that in.
That looks like bleach.
You think it is? Here, take a whiff.
Maybe. Yeah, it smells like chlorine.
Why did you do it like that?
Well, if I put it up to my nose might get irritated.
Yeah, so that's the way chemists, they check the odor or something by doing like that, taking a whiff. Okay, I'll hold the two plates. You pour the bleach into the beaker and watch what happens to the meter.
Okay. It goes up. Well, how come? Because
Yeah,
bleach
keep
is a
going, keep
base.
going, keep going. Go all the way to the end. Okay, that's good, fine.
Bleach
what
is
was
a
your
base,
question?
though. How come? Bleach is a base.
Yes, but most people think that in order to make a battery you need an acid, and you don't really need one. All you need is an active chemical. And in this case, it's a base, and there are some bases that are very active. In fact, one is called lye, that's so active. It's used for oven cleaners and things like that because it'll eat right through your skin. It's very
Whoa.
active. So the chemical in bleach is active enough with two dissimilar metals to produce a very good wet cell. In fact, it's gone
Yeah.
right off. It's gone right off the
Whoa,
scale, isn't
yeah.
it? In fact, we can control it by varying it like that. Anyway, now when somebody says, "How do you make a wet cell to generate electricity?" What are you going to say?
You need two dissimilar metals and an active chemical,
Which can be an acid.
acid or a base.
Right. You take medicine by swallowing it as a pill or as a liquid. A nurse or doctor can give you medicine with a hypodermic syringe. Now there's another way. You can wear it. It will deliver medicine to his heart by diffusing through a special membrane into his skin, then into his bloodstream, and onto his heart. So far, only a few medicines can be taken by wearing them. Look at all the water down there, Alan.
Whoa,
Yeah.
the plant give out this much water?
Yeah, well, they actually give off a lot more than that. And notice where it's coming from? Remember I said it was going to come from the leaves? You can see all the moisture on the inside, see it?
Yeah, there's little drops.
There's a
all
little
over the
drop
place.
going down right now, yes. Now, all plants give off water like that, some more than others. It's, scientists have measured the water coming from a corn plant, for example, and it gives off a couple of liters a day, depending on the temperature and the humidity. If you want to do this at home, you don't have to do it around a tree branch. You can do it around a plant, you know, an indoor plant.
Oh, so that's why in a forest it's so damp and moist.
Right, because all the trees are giving off a lot of moisture, right? So if you want to try this at home, just carefully cover a plant and you'll see that they give off a tremendous amount of water. This is a leech, often called a bloodsucker. It's not a rare animal, but it is rather unusual. It has, in effect, a series of brains. Dr. Charles Lent studies these relatively simple animals at Utah State University. The cluster of about 400 nerve cells that make up each of its brains controls complex behavior. A leech can sense a difference of 1/10 of a degree in its search for a place to make an incision from which to suck blood. Nerves in its body wall signal the brains when the leech is stretched full of blood. Only then does it stop feeding. Look at the difference in size between a hungry leech and a well-fed one. Studying these animals with relatively simple brains could give scientists clues to the function of more complex brains, including those of humans. A valuable research animal, the leech.
Whoa!
That is what I call an explosion, right?
Yeah. Okay. What happened? How did that do that?
Well, here, you can take the safety glasses off temporarily. You can see why I had you wear safety glasses,
yeah.
too. This is a very famous sort of chemical reaction that is a combination of hydrogen and oxygen, and is pretty dangerous, so you won't be able to try this at home because you can't get the hydrogen. But it's the one that science teachers have a lot of fun with. Basically what it is a can that's made of cardboard, see? And here's the top, which I've cut a hole in, see? Okay. The bottom also has a little hole. Okay?
Oh, yeah.
And what we're going to do is fill it full of hydrogen, then put the
lid on the bottom.
Lid like that, and put it down here like this, and then light it up here. Okay. Now, because the flame is going up here, air is coming in through the hole down here.
And mixing it with the hydrogen?
And mixing with the hydrogen. And there's a continual kind of mixture as the air flows in here until finally when it gets to be just the right combination of hydrogen and oxygen, pow!
Boom.
And you know what we're making, by the way? Water.
Water?
H2O. We're combining hydrogen and oxygen.
Really?
Oh, a little tiny drop, but that's what it...
How come you have it up here on the
Well, that's
boards?
so the air can certainly get through the hole.
Oh,
okay.
Otherwise
you
it
get
was
the idea?
down against. Yeah.
Okay, so back with the safety glasses. Now let's try again and do the famous hydrogen bomb. Okay, are you ready? Got your safety glasses on? Okay. In goes the hydrogen. Put your finger over the top there, will you? Now remember, you never know when it's going to happen because it takes a while for the mixture to go. Okay, take your finger off and step back.
There it goes. I saw a little flame that time.
Did you? Ah, okay. So it's a very dangerous experiment which you will not try, but which I think you will enjoy very much when your science teacher does it.